To start with, I would like to add a few remarks about coordinate transformations in phase space and generalize the concept of coordinate transformations a little bit further. So far, what we've considered were coordinate transformations in phase space. So we have old coordinates, Q and P, and we have a transformation that transform these into new coordinates. We call them capital Q, capital P in phase space. We allowed these transformations to be time dependent. And these were the most general transformations that we considered so far. And then we focused on a particular class of transformations, namely those that are canonical. So let me first briefly summarize where we stand. We considered transformations from old to new coordinates in phase space, and these transformations, we allowed them to be time dependent. We focused on transformations that are canonical, and such a transformation is canonical if the following condition is met, namely that there exist functions h prime and g such that the sum over I, pi dqi in the old coordinates minus sum over I pi dqi in the new coordinates plus the difference h prime minus h dt, where h is the Hamilton function in the original coordinates and h primed is the Hamilton function in the new coordinates. So if that expression is some total differential of some function g. So if we have original coordinates with little letters and we have new coordinates with capital letters, in the original coordinates we have Hamilton function h. Then if there exist functions h prime and g such that this relation holds, then the transformation is canonical, and then h prime is the Hamilton function in the new coordinates. That's where we stand at the moment. Now we generalize that, and in addition to transformations of Q and P, we also allow transformations of time. So now we allow, in addition, transformation of time from little t to capital T. So we redefine our time coordinate. And together, this is now a coordinate transformation no longer in regular phase space, but this is now a coordinate transformation in extended phase space, which is ordinary phase space with the additional time coordinate. So this becomes now a coordinate transformation in extended phase space. Now we also have to then reformulate our criterion for this transformation to be canonical. We have, in the original criterion, we have only the original time coordinate, little t, appearing. Now we need a criterion that includes the new time coordinate. And the way this is generalized is that you replace this expression here by h prime d capital T. So it's the new Hamilton function times the new time differential, d capital T, minus the old Hamilton function and the old time differential. So it follows the same pattern as for the q's and the p's, configuration and momentum coordinates. There you also have PDQ in the old coordinates versus PDQ in the new coordinates. Here you have HDT in the new coordinates and HDT in the old coordinates. So this is the generalization of canonical transformations that includes also transformations of time. Now in the new coordinates, if the transformation is canonical, the system still obeys Hamilton's equations, and they take the following form. Qi dot, change of the configuration in the new coordinates, being defined now as the total time derivative of Qi with respect to the new time, capital T. This is given by the partial of the new Hamilton function with respect to the new momentum at fixed configuration and time, or both in the new coordinates. And likewise for the change in momentum, again, that's defined as the total time derivative of the new momentum coordinate with respect to the new time. This is minus the usual structure, partial of the new Hamilton function with respect to the new coordinate at fixed p and t. So this is the first addition that I want to make to our earlier discussion of canonical transformation. We extend the concept to include transformations of time. Then another addition that I would like to make, namely the distinction between so-called passive and active transformations. I would like to illustrate that with a little sketch. Think of a particle in a Cartesian coordinate system. The dot is the particle, 2 dimensions, and then the particle has this position vector here, and the axes represent the reference frame. Now, relative to this reference frame, the particle has coordinates x and y. Now we can consider two kinds of transformations. We can either say we change our reference frame, we change coordinates. So from the original coordinate system with these axes, we go to a new coordinate system that is rotated against the original coordinate system. So we rotate the axes of our coordinate system, and the particle, however, is still at its original position. It remains where it was. And then, of course, with respect relative to the new coordinate system, it has now new coordinates. It now has coordinates x prime and y prime. So the coordinates of the particle have changed because we have changed the reference frame. Such a transformation where the physical system stays where it is, but the reference frame or the coordinates change, are called passive transformations. Alternatively, we could have done the following. Alternatively, we could have kept the reference frame, the original coordinates, but we could have rotated the particle instead. So we could have gone to we could have rotated the particle to a new position here, and in there we have new coordinates x prime and y primed. And I tried to draw the pictures in such a way that in both cases, at the end we have the same coordinates, x prime and y primed. Only that in the first case we fixed the particle and we rotated the coordinate system. And in the second case we kept the coordinate system and we rotated the particle. But in terms of the coordinates, the result is the same. In both cases you have new coordinates x prime and y prime. The second case is called an active transformation, where you rotate the particle rather than the coordinate system. The key message here is, first of all, that you understand the difference between active and passive, so you know about these two concepts, and that they are equivalent pictures, so that whenever you have a change in coordinates, you can interpret them either as an active transformation or as a passive transformation. In a way, we already encountered this when we considered the time evolution of the system as a canonical transformation. When we have the time evolution of a system, of course the coordinates of the particles, of the bodies, change in time. And we can, just like here, we can regard this either as resulting from the particle actually moving in a fixed coordinate system, that would be the active picture, or we could regard this as the result of our coordinates changing in time, and the system is actually fixed, but the coordinates change all the time. And that is the picture that you have when you regard time evolution as a time-dependent canonical transformation, when we had talked about that. That would be the passive picture. So you say, actually, the system is in rest, but we describe time evolution as a time-dependent canonical transformation. And as a result, the coordinates of the particle change all the time. And that would be the passive picture. Then next, let us look at coordinate transformations in the generalized sense that we had just discussed, namely including possibly time transformations in extended phase space, but limited to canonical transformations. So I would like to sketch extended phase space. Consider a body that is originally at this point here. This is an event at some time t, and position from configuration q and momentum p. So this is a point in extended phase space. And now let's consider a transformation of these coordinates. And drawing on what I had just said, I would like to do that in the active picture. So, and that because that's also easier to visualize. We are now in the active picture where we actually move the physical system rather than shift the coordinates. So we take that blue point here and we move it to a different point, the red point here. And this red point now has new coordinates, both time, and we say that time shifts infinitesimally by some epsilon times phi, where epsilon is an infinitesimal parameter, and configuration. Let's say the configuration changes from q to q plus some infinitesimal parameter epsilon times psi. And finally we also have a new momentum, which is the original momentum p plus some epsilon times chi. So we have a transformation that shifts points in extended phase space to infinitesimally to neighboring points. Here the blue point to the red point. And remember, we are in the active picture, so we're actually shifting points. We keep the coordinate system fixed, and we actually shift points actively in extended phase space, but you could just as well also regard this in the passive picture where the point is fixed but you shift the coordinates. So what we have here is a transformation in extended phase space of the following form. The time coordinate t goes to t plus some infinitesimal parameter epsilon times some function phi. Function is now a sort of a finite function, phi, which may depend on q, p, and t. So in other words, all the points in extended phase space are transformed differently, or at least it's allowed that each point in extended phase space is shifted in a slightly different way. So depending on the position of the point in extended phase space, q, p, and t, there is a shift, an infinitesimal shift, to a different point. And that shift can be different for all points. And in the same way, you shift the configuration that's described by a function psi, and momentum that's described by a function chi. And the epsilon is an infinitesimal parameter, and these are finite functions. Now, we said earlier that this transformation, this infinitesimal transformation, is canonical if there exist functions h prime and g such that pdq minus the new coordinates. Now the new coordinates are the shifted coordinates as defined above. So the new momentum is p plus epsilon chi. The new configuration is q plus epsilon psi. And then we have h prime, which, if the condition is satisfied, would be the new Hamilton function in the new coordinates, times dt, the new dt. The new dt is the original dt plus epsilon d phi minus h dt, the original coordinates, if that is some total differential of some function g. And that will, because the transformation that we consider is infinitesimal, so on the left-hand side we have all the epsilons, it's infinitesimal, to make clear that we expect the right-hand side also to be infinitesimal. I also introduce the parameter epsilon on the right-hand side and say this is epsilon times some differential d of some finite function g. At this point, I would like to exploit the fact that the transformation is infinitesimal. So I would like to limit myself to lowest order in epsilon, lowest interesting order in epsilon, which is first order in epsilon. So to lowest, meaning first order in epsilon, and also to lowest order in h prime minus h. Because if we have an infinitesimal transformation of our coordinates, then the resulting transformation of the Hamilton function will also be infinitesimal. So h prime minus h, we expect, will also be of the order epsilon, and therefore we also work in lowest order, in first order in h prime minus h. So we drop all the higher order terms, and then this condition above turns into the following condition. We have h prime minus h dt minus epsilon times, and then we have two first order in epsilon. We have a chi dq, we have a p d psi, and we have minus h d phi. And on the right hand side we have our epsilon times dg. So how does the result come about? On the left hand side, you see when you multiply out the brackets that you have from the previous line, then the first product of the two brackets, you get a PDQ that cancels with the PDQ in front. Then you get two terms that are of the order epsilon, namely minus epsilon chi dq. That's what you also find on the last line. Then you have minus epsilon p d psi. That's also what you find on the last line. And then you have a term of the order epsilon squared, and that has been dropped. Then what else do you have? We move on to the terms with the Hamilton functions. When you multiply out the bracket, then first you have h prime dt, and this minus the h dt gives the term in front of the last line, h prime minus h in brackets times dt. And then you have h primed epsilon d phi, but to lowest order in epsilon, you can replace h prime by h. And this becomes epsilon h d phi, which I have in the last line I've taken into this curly bracket. Right, and on the right hand side you have the epsilon times dg. So this is the condition. Sort of initially we had defined these coordinate transformations in extended phase space. These could be arbitrary shifts. This imposes a condition so that this infinitesimal transformation is canonical. This means that these functions that characterize the coordinate transformation, so the phi, psi, and chi, that these functions are actually not independent. Only two of them are independent, phi and psi, and the chi follows from the other two functions. One way you can see that is that you take the differentials d psi and d phi and you expand them in differentials of the coordinates dq, dp, and dt. So, for example, you expand d psi, that would be d partial psi with respect to q dq plus partial psi with respect to p dp plus the partial of psi with respect to t dt. And you do that also for phi. You insert that into the condition that we have above. And then we have on the left-hand side, we have a linear combination of differentials, dt, dq, and dp. On the right-hand side, we do the same for the function g. We also expand it in differentials dq, dp, and dt. these differentials are independent, linearly independent. The dq's, dp's, and dt's, they're linearly independent. And then you can compare coefficients. So in order for this condition to hold, the coefficients in terms of the dq's, dp's, and dt's must match. So you compare coefficients. And this implies, if you look, for example, if you look at the coefficients in front of the dq, then this implies that the function chi must be given by minus p partial of psi with respect to q plus the Hamilton function times the partial of phi with respect to q minus the partial of g with respect to q. So you see that the various functions that appear here are not independent, but if you are given the function phi and psi that characterize the shifts in time and configuration, and you are also given the Hamilton function and this function g, then these determine the function chi to ensure that the transformation is canonical. Okay, so far we've talked about coordinate transformations. Now we come to the issue of symmetry. One says that there is a symmetry in the system, or that the coordinate transformation constitutes or represents a symmetry if the coordinate transformation maps physical trajectories to physical trajectories, which are governed by the same Hamilton function. How can we capture that mathematically? Here I'd like to come back to my favorite drawing. Remember, in extended phase space, you remember this picture. I like pasta, so I always have to think of rigatoni when I draw this. So these are physical trajectories in extended phase space. So this here is this tube of physical trajectories governed by some Hamilton function h. Physical trajectories means that they satisfy the Hamilton equations. And this, we had discussed earlier, is equivalent to the statement that there is this Poincaré-Cartan invariant, that the integral around the closed loop, around this tube, so let me indicate such a loop. That could be, say, this loop here. So any loop around this rigatoni gives the same result, and it doesn't have to. The loop doesn't have to be at constant time, so it can be tilted in any way. So on this loop, you can have points in extended phase space with different time coordinates. So what is it that you integrate around the loop? You integrate p dq minus Hamilton function, which itself is a function of q, p, and t, dt, that is invariant along the tube. That's what we mean by physical trajectories. So these are different ways how we can characterize physical trajectories. Now we perform our coordinate transformation, and we do that again in the active picture. In the active picture, we take arbitrary points in extended phase space, and we shift them as we did before. So the blue point gets shifted to the red point. And we do that for all the points in extended phase space. In particular, we do that for all the points on this tube. So as an end result, the entire tube gets shifted. And we end up with a new tube that might look like that. And the orange loop around the tube will also become shifted and will become a loop around the shifted tube. So it might then look like that. This is our new loop around the shifted tube. Now, what our symmetry requirement says that the shifted tube must again consist of physical trajectories. And these trajectories must be governed by the same Hamilton function. So what we require here is that these are physical too with the same Hamilton function. What does that mean mathematically? Mathematically that means, in particular, in the original loop, the original tube, we had this invariant loop integral, this Poincare-Cartan invariant, this invariant loop integral. Now all the loops get mapped to loops around the new tube, and around the new tube, the shifted tube, these loop integrals must still be invariant along the new tube. So the difference of loop integrals around the shifted tube and the old tube, this can be at most a constant. So the mathematical condition for this requirement is that the integral, the loop integral around the shifted loop, where we have, rather than p dq, we have the shifted p and the shifted q. So we have p plus epsilon chi, that's the shifted p, and then we have dq plus epsilon d psi minus, then we require that that the new trajectories are governed by the same Hamilton function. So we have the same Hamilton function h, but it's now evaluated on the shifted loop. So the arguments have shifted. So and instead of q, p and t, we must insert the shifted q plus epsilon psi, the shifted p plus epsilon chi, and the shifted t plus epsilon phi. And then we have a dt, and the time has also shifted. The new time differential, that's dt plus epsilon d phi. Now this is the integral around the shifted loop. This must equal, if this is to be a symmetry and really physical trajectories are mapped to physical trajectories, this must equal the integral around the original loop. So this must equal the loop integral p dq minus h evaluated at the original coordinates q, p, and t, dt, possibly up to a constant. If that is the case, then if along the original tube that loop integral is an invariant, then along the shifted tube, the transformed tube, the loop integral will still be an invariant. So this condition must hold for all loops around the tube. Now we exploit the fact that these transformations are infinitesimal. We focus on lowest order, that is first order in epsilon. So to lowest, i.e. first order in epsilon, this requirement takes the following form. The integral around any closed loop around the tube, and then we have epsilon chi dq plus epsilon p d psi minus epsilon h d phi. This comes from multiplying the brackets and keeping only the first order terms in epsilon. And also what I do now, going from the previous requirement to this new requirement, I take the new loop integral minus the old loop integral, and then terms cancel, and what I write are the remaining terms, which are first order in epsilon. Then, so you get these three terms, and then you get terms that come from the fact that you, in the new loop integral, you have to evaluate the Hamilton function in the shifted coordinates, and you also expand that to first order in epsilon around the original coordinates, and you get partial derivatives. So you get a term of the form epsilon partial h with respect to q psi dt. You get a term epsilon partial with respect to p chi dt, and you get a term proportional to epsilon partial with respect to t phi dt. So these are all the terms that you get when you take the difference between the two loop integrals. The requirement says that this must be a constant at most, or zero, at most a constant. If we require that the transformation is canonical, then you may recognize these first three terms on the previous page. These are also the terms that appear in the curly bracket, in this equation with the curly bracket. There you have chi dq plus p d psi minus h d phi, the whole thing times epsilon. This is, if this transformation is canonical, this must be equal to h prime minus h dt minus epsilon dg. And this we can use here in the symmetry requirement. We can say this is h prime minus h dt minus epsilon dg, if the transformation is canonical. The requirement that the transformation be canonical states that there must exist functions h prime and g such that the terms underbraced in blue, with this blue underbrace, that these terms can be written as h prime minus h times dt minus epsilon dg. So that's the requirement that is canonical, that such h prime and g exist. Yeah? Where this does not mean that h prime is now a different Hamilton function for the shifted physical trajectories. It's only the mathematical criterion for the transformation being canonical that such functions h prime and g must exist. The contribution dg, this term does not contribute to the loop integral because the integral over a closed loop of a total differential is 0. What we can now say is that a loop integral over the remaining terms, that must be equal to 0. In the loop integral, in the integrand, we only have terms proportional to dt. We have h prime minus h dt minus epsilon times this square bracket times dt. Now the loop integral must be the same for all loops around the tube. As a special case, we can consider loops that lie in the plane of constant time. So we can consider a loop where all points on the loop have the same time coordinate. Therefore, on such a loop, dt is equal to 0, and therefore this integral will be equal to 0. So, in fact, we can say that this constant is actually equal to 0. So the symmetry requirement says that h prime minus h and this term here, epsilon times the square bracket, that these two terms must be equal. If these two terms are equal, then they cancel, and the loop integral is always 0.